These are your 9-2 video notes for day 2 of dot product, which is applications of dot product. Day 1 was mainly just to get you guys used to how you do it, the straightforward calculation where you multiply components, A times A, B times B, and add them. It was also to talk about how we use dot product to find some things like the angle between our vectors perpendicular to each other based on their dot product, and also a component of one vector along the other, which was a shadow idea, so the shadow length. As you go to day 2, what's the application of component? And component is the big part here, so we want to again talk about, in this case, force instead of length. So when we go magnitude this time, we're going to be talking about weight. And what we're going to do is take our alternative version of dot product formula, and we're going to kind of just sort of manipulate a little bit to work on this image here. So the weight of the vehicle is the red vector. What we're trying to figure out is how much of its force is applied parallel to the driveway and perpendicular. Well, you know, so far we've been basically looking at moving some object, force applied to an object that moves it across kind of a flat surface or horizontal. So all we really would do would take its magnitude and its theta with the ground, let's say, and we just do components. So magnitude cosine for A, magnitude sine, excuse me, for B. And here that'd be how much of it's the force I'm applying at that particular angle. But now your object's on an incline. So that changes a little bit of the way we think about it, and we have to go to a component version of the problem. Component of u along v, I should say. So we're going to kind of manipulate this formula a little bit. We'll start with that. So I'm going to use the w and the u vectors. And so if I work this formula with w and u, what I'm figuring out here is how much of the vehicle's weight is applied in the direction of u, or what's the component of w along u, which is the formula from day 1. And then what I'm doing here is I'm just solving it for this expression. So basically dividing by the magnitude of u, leaving me with magnitude cosine. That actually is another way of calculating the component of w along u, which is actually going to be easier for us because we're going to be giving you guys a weight and we're going to be giving you a theta. The key is, where is the theta? And as I pop this up, you notice that that's the theta between those two vectors. So whenever you use a formula like this, make sure you're using the theta between the two vectors. Now switch your thought process over to w and v. Well, if I divide both sides by the magnitude of v, which creates the component formula from day 1, I get magnitude cosine theta again. But look where theta is now. It's sitting between those two vectors. So the formula is going to be the same. I give you the vehicle's weight, or whatever the object is, on an incline, and I ask you how much of its weight is being applied parallel to the surface or perpendicular, and the formula is identical except the thetas are different. Now if you want to use the shadow concept, let's do the shadow quick. So let's say we're doing the first one, and we're doing w onto u. So sun hits vector w, and when it hits vector w and goes perpendicular to u, you can see that little dashed line there. Well, that actually be the force applied, how much of this weight is being applied in that direction. Now, yesterday we talked about it as length, so a shadow was length. Today the shadow is a shadow force, I guess I'll put it that way. And then same thing here, if I'm hitting the tip of w but going perpendicular to v, then that is a shadow force. Now, in terms of forces, the force here is much greater than it is here, and we'll explain that in just a minute. So we'll get into why that is in a second. Okay. So let's do the actual problem with some numbers. So we got a 300-pound vehicle, 3,000-pound vehicle. Incline is 10 degrees. Let's start out with my incline. So incline is here. Now, that is neither the angle here or here, at least not at the moment anyway. So when we go to do our magnitude cosine thetas, and we're trying to make sure between certain vectors, we've got to make sure we have the correct theta. The force needed to prevent the car from rolling down the driveway, well, that's talking about this force. Now, it's kind of like an opposing idea, so really it's based on the incline, of course, but also the vehicle's weight, which of course makes a difference, and then the actual stuff in the car, like your emergency brake and your transmission when it's put in park. Those things all locked together will take care of that and keep your vehicle from moving. And the friction of your tires and the surface, there's a whole lot of stuff involved, but we're going to keep it real simple. Just talk about it as how the weight's applied and in what direction. So if we're going to do between w and u, how much of the vehicle's weight applied along the surface of the driveway, we've got to have the theta up here. Well, if that's 10, that's a right angle, then that's going to be my theta. So I got to make sure I use 80 and not 10 when I do this calculation. On the other hand, if we say how much of the vehicle's weight is applied perpendicular to the surface, and that's more like just pressing against the driveway. So how much of the weight is actually pressing against the driveway? That's going to be the 10 degrees. And for a simple reason, because u and v form a right angle, so if that's 80, then that's going to be 10 degrees. So I make sure I use 10 when I do that calculation. Now, in terms of just talking about what's going on here with the weights, why is this one so much bigger than this one? Well, kind of a simple reason. If you think about the angle itself, a 10-degree incline is pretty slight, so it shouldn't take a whole lot of force to offset the vehicle's weight to keep it rolling down the hill. I mean, literally, if my driveway was fairly gradual, I could probably take my truck out of park, the emergency brake off, and I could probably just stand behind it with one hand on it and hold it in place. My neighbors would be like, what in the heck is going on here? But if the incline was really slight, I could do it. Now, if the incline is quite steep, then there's no way I can hold that vehicle back. So most of the weight is applied vertically against the driveway because you just don't have much of an incline going on. You increase this a lot, then these numbers are going to start to change. Also in this problem, we're asking you to find the offsetting kind of forces, but we can ask you one of three things. So I could give you the vehicle's weight and this force and ask you to figure out the theta, and then ask you for the incline. You'd have to figure out that's subtracting from 90. I could give you the weight it takes to prevent it from rolling back and the incline, and ask you to come up with the vehicle's original weight. So any one, if you kind of put an equation together, these three numbers, I can solve for any one or ask you to solve for any one. So keep that in mind as you're working through the problems. It may not always be that you're just finding the forces. You might be finding theta, and then turn into an incline. You might be finding the vehicle's original weight, or whatever the object is. Okay, so that's a component of one vector law and the other, but this time we're on an incline. Then there's projection. Well, projection is really a step up from shadow. So the shadow, remember, was the component of u along v. So how much of u's length is in the direction of v, but that was another length or another magnitude. So cast our shadow. Shadow hits, right, creates a distance or a magnitude, but now what's that as a vector? Like, what are its actual a and b components? And the projection vector is that vector. So that's a shadow vector. So projection of u onto v is the vector created by, or the vector that corresponds to the component of u onto v. Okay, let's build up projection. So the projection formula is derived from doing a little bit of just straight unit circle work, unit vector work. So when we do unit vector, that is a vector with a magnitude 1. So we want to say, if we look at this vector, what is its unit vector? Unit vector and the original should point in the same direction, but the unit vector should have a magnitude 1. If you guys go ahead and just do magnitude of this, clearly it's not a magnitude of 1, it's the square root of 13. So what we want to do is figure out what is the unit vector that corresponds to this, and then what is, well, we'll double check the magnitude in a minute. So that symbol is for unit vector. Basically we do 1 over the magnitude of the original and multiply it. It's like a fraction of the vector's length, that's kind of what it amounts to. And then get that vector. So there's the actual unit vector. So I'll pop it up in a sec, but what we're going to do is do its magnitude. And when we do that, we'll notice that it points in the same direction it always would be, so parallel to the original, and it actually has a length or a magnitude of 1. If you do that calculation, you're going to get a 1. So we need that. This is important. I'll talk about this in a second. We need the unit vector to get our projection vector head in the right direction, because if we just base it on the component, that's only a length, but length of what and where and what direction are we going? So as we start to put it all together, here's how it works. To do the projection formula, we've got to do component of u along v, so that gives us a length, so a magnitude. But then we got to multiply it by the unit vector, which then gets us headed in the right direction, the same direction as v. So if we're going to project, like u1 is the projection vector, we're going to project it onto v and get it going in this direction. The length could be any, the length, if I say this has got a length of 10, 10 what? 10 where? 10 in this direction. So that's the unit vector does, because the unit vector is always in the same direction as its original vector. So we kind of combine this stuff, mash it together, and now we got our formula for projection vector, And then we'll do a little bit of resolving forces, or resolving vectors into parallel and perpendicular components. Parallel and perpendicular vectors, I should say. And I'll show you that in a minute. We don't need to do that just yet. We'll get a visual going for that. All right, well, let's kind of get the problem working, give you guys the visual aspect of everything and see how it works. So the projection of u onto v. Now, let's just do shadow for a sec. If I was to cast a shadow, which I'll do in a second, right? Its length, the shadow's length would be the component. The vector itself would be the projection. So we need some stuff, right? We need to know what's the magnitude. We know what's the dot product. Throw them into the overall formula. Clean up the formula a little bit. That's actually a half there. And then here comes my projection vector. So if I do the sun idea and cast a shadow, look where it hits. So the length of this is the component of u, how much of u's length in the direction of v. And then the unit vector attached to the overall formula we talked about on the last slide gets us going in the correct direction. Now, the other thing to do is for us to kind of undo this a little bit and say, well, u1 parallel to v, what is it as a vector? and u2 perpendicular to v, what is that as a vector? Well, we already have this one. Projection vector is the parallel vector. Okay, it would always go in the same direction. So we've already got that. You'll see what I mean by that in a second. And then perpendicular, which isn't really here yet, we're going to pop that up, would be the subtraction of those two. And the reason being is pretty simple because, let me show you this first, then we'll go back and talk about it. So u1 parallel to v, excuse me, u2 perpendicular to v. If I actually took u1 plus u2, let's say I slid the green over here like tail to head, guess what? I'd have u. So u1 plus u2 should always produce the original vector, and turns out u1 is parallel to v, u2 is perpendicular. And so really it's a matter of just kind of quick calculation with the components. And you can see again right there, right angle. So kind of a whole big package of stuff to look at here, but projection vector is kind of the most important thing. And then how do we go parallel or perpendicular to the original vector? What are they? All right, let's get into our final concepts here. Our final concept is work. So work actually is basically what it says, right? It's what total amount of work or effort it requires to perform a task, move an object through a distance. And so work has to be felt. And I'm going to talk to you guys about that once we get done with all the calculation and all the problem itself. We'll go back and talk about it. So we'll try to make some sense out of it as how would you understand work as a number. But let's just get the problem done first. So basically we're going to have two things going on. Work is the dot product of force and displacement. So force applied, but also applied over a distance. You'll need to have those two vectors. So we'll do a distance vector and a force vector, and then we'll dot them. And that number will represent our work, and then I'll talk about again what that actually means as a number in a second. Well, if you're moving an object horizontally through a distance of 200, then displacement vector is pretty simple. It's all horizontal, no vertical, right? You mean just pulling that wagon across that distance. The force vector we do have to do like we did in 9.1, magnitude cosine, magnitude sine, because again, a pulling idea. Now, pulling compared to pushing, right? So our vertical is up, so that gives us a positive vertical component. So magnitude cosine, magnitude sine, just like day one of talking about vectors. And then we'll do some numbers here to kind of clean it up. And then we dot that. So again, we do 200 times 19.28 and 0 times 22.98. And we get 3856 foot-pounds. So there's actually the work. Now, what does it mean, right? So the only way I can describe this to you guys is if you had a wagon, and let's say you put your little brother or sister in it, and they weigh like 60 pounds, let's say 50 pounds, and you pull them, and you pull them for 200 feet in that wagon, and then you go back to the same starting point, and you put like your mom and dad in the wagon together, and you try to pull them. You guys know for sure that I'm sure you felt it at some point in your life, the difference between doing like pulling something that's light and pulling something that's really heavy. Well, the difference in 200 feet of pulling your little sister or brother and 200 feet of pulling mom and dad in a wagon is what work feels like, the effort required to perform the task. And so that's the only thing I really tell you guys about giving this number some meaning, is it feels like you've done a certain amount of work, right? So that'd be a way to kind of quantify it. Otherwise, you look at this number and go, what does that mean? Well, that's the work it takes to move this object through this distance, and you'd have to feel that work. Okay, and that's the end of the day 2 notes for 9.2 applications of dot product.